study it later. All right. So today we try to finish chapter 4, okay? And please take out your calculator, okay? Take out your calculator. And today we need to do some math. And also, again, if you have any question, just type in the chat window, and then if I saw it, okay, so I will answer you immediately, okay. All right, and so last time, we just talked about kind of your cyclic molecule, and so just keep in mind, okay, so if it's a cyclic hexene case in a chair conformation, so please convert it to a planar structure. This is a wedge or dash structure, and then either you can assign RS for all the chiral centers, or kind of compare the two molecular relationships, okay. So that will make your life much easier, okay. Yeah, please keep in mind, okay. All right, so and then one announcement, okay. So after this lecture, okay, so you can start work on Nanomi VR worksheet, okay. So library will install some kind of Nanomi program, okay, and then you just put on headset, okay. So here's kind of a picture I took like maybe 3 years ago, okay. So nowadays kind of they have much better headset, okay. So wireless one, okay. There's no long cable, okay. And then there are about 4 or maybe 5 questions, okay. So you play around some kind of molecule and then complete these questions, okay. So that will be 10 points, okay. And so before, just one thing, please keep in mind before you work on the Nanomi worksheet, okay. Please watch online video, okay. So this video I already post on EduCat, okay. So have a little bit of basic idea how to operate the instrument, okay, how to open the program, okay, how to move molecule, how to expand it, how to rotate, okay. And later I will send out another email, okay, probably later today, okay, so give you more detailed instruction how do you kind of make reservations, okay. And just the easy money for you guys, just extra 10 points, okay, so All right, okay, let's continue our lecture. And now we need to talk a little bit about physical property of the isomers. Okay, so we already learned kind of constitutive isomer. So like this the butanol and also the THF. Okay, so same polymer but totally different arrangement of the different connection of the atoms. Okay, and those just different compound. Okay, they have a different kind of physical property and also chemical property. Okay? So big difference there kind of melting point and boiling point. Okay. And the same thing also true for the diastereomer. Diastereomer, okay. So diastereomer, we learned kind of the multiple stereocenters, okay. So some same, okay, some different, okay. For example, this is the 2R3R tartaric acid and 2R3S tartaric acid, okay. So you can see kind of some stereocenter, opposite, some stereocenter, same assignment, okay. And then diastereomer, okay. So diastereomer similar like the constitutive isomer, okay. So they have different kind of physical properties. Okay, so and you can see here. Okay, so they have different the melting point. Okay, different boiling point. Okay, for the 2R, 3R versus kind of 2R, 3S. Okay, so also they have different chemical reactions. Okay, so that's we will learn kind of in organic chemistry too. Okay, and next kind of very interesting is enantiomers. Okay, so enantiomer because they are totally just a mirror imaging to each other. Okay, they're very similar structure. Okay, so then they will have same melting point, same boiling point, same kind of solubility, same kind of heat combustion, and everything pretty much same. Okay, so here's kind of example for the 2R3R tartaric acid and also 2S3S tartaric acid. Okay, so you see kind of all the stereocenter are opposite. Okay, so one's RR, one's SS. Okay. So they have exactly the same melting point, same density, okay, and then pretty much same thing. Okay, so it's very hard kind of to distinguish a pair of enantiomers. Okay, so you can only distinguish them kind of in chiral environment. Chiral environment case, for example, solubility in the chiral solvent or kind of reaction rate difference in the chiral region. Okay. However, okay, there are one special region, the case with one special kind of physical way can distinguish kind of enantiomers. Okay, so that we use kind of polarimeter. Okay, so and before we learn the parameter, okay, so we first learn what's plane polarized light, plane polarized light. Okay, so normally speaking, kind of for ordinary light, okay, for ordinary light, okay, like our sunlight, okay, lamp light, okay, so they vibrate all the directions, okay, so like here the left, okay, so the all directions just move forward, okay, and so but here the for polarized light, okay, so only vibrate only one single kind of direction, okay, so like this one, okay. And so in this case, for chiral molecule, okay, and can rotate this plane polarized light into certain degrees, okay. For example, once coming is kind of 0 degrees, okay, but here once this plane polarized light pass through kind of chiral molecule, okay, and then we can call this the plane polarized light kind of rotate maybe like a 10 degree, 20 degree, whatever, okay. So then we can call this compound called kind of optical active, okay, optical active, okay. So chiral molecule expect kind of optically active, okay. So let's do this, So quite often you will see kind of in the literature or maybe in our future exam quiz, okay, the people always say kind of optically active, okay. So that's actually equals to kind of chiral, okay. Yeah. So if in exam quiz I ask kind of which molecule is kind of optically active, okay, and then you just equals kind of chiral. I ask kind of which molecules kind of the chiral, okay. So normally physics okay, like use the optically active, okay. So but for chemistry case like use chiral. Yeah, that's something please keep in mind. Yeah. All right. And here's kind of a setup here for plane polarized light. Okay. And there's kind of the light resource. Okay. So normally it's kind of a sodium lamp. Okay. And pass through kind of polarizer. Okay. So original kind of this lamp give ordinary light. Okay. And then vibrates the all direction. Okay. But once the pass through kind of polarizer. Okay. And then generate the plane polarized light. Okay only one direction, okay? So light can vibrate only one direction, okay? And then, you put your sample in the sample cell, or here's kind of sample tube, okay? So normally it's kind of a liquid sample, okay? So either solution or kind of pure liquid, okay? And if this sample is chiral, also called kind of kind of optically active, okay? It will rotate this kind of plane polarized light in certain degrees, okay? Right, in certain degrees, okay? And then there's kind of detector can detect kind of how many degrees okay, your sample rotate this plane polarized light, okay? And when I was a student, okay, and I use this kind of manual parameter, okay, parameter, okay, so has kind of manually adjust kind of the light kind of degrees, okay, and then measure kind of how many degrees kind of rotate this plane polarized light, okay. And so nowadays, kind of it's more kind of advanced. Okay, so digital one. Okay, so you put your sample in the sample cell, and then instrument can automatically read how many degrees kind of rotate for this kind of prime power light. Okay, so in the current environment, we have the middle one, and then if you go to kind of some research school, they have kind of more advanced kind of digital one. Okay, so. All right, okay, so for one chiral molecule, we will rotate kind of polarized kind of light at a different degree from kind of another polar molecule, okay? For example, telluric acid and also kind of maybe chiral molecule and then another kind of chiral molecule rotate different degrees, okay? And we actually can quantify this kind of the degrees, okay? So how many degrees, okay? This is actually pretty important property for chiral molecule, okay? Chiral molecule, okay? And then we come to kind of called specific rotation case. So before we talk about the specific rotation case, so let me see. Yeah. So some concept case if molecule case so rotate the plane polarized light kind of clockwise okay, and then we call kind of dextrorotatory case. And if we kind of rotate the plane polarized light kind of counterclockwise okay, we call kind of level rotary. Okay, so yeah, maybe just nothing we need probably 没到那看到 important okay. So if yeah, one compound rotated yeah, plane polarized light kind of the clockwise, then we call it kind of yeah, dextro rotary, dextro rotary. And quite often, yeah, people use the D or kind of just a plus sign indicated this kind of yeah, dextro rotary. Okay. If it's counterclockwise, okay, then yeah, that's people call it kind of yeah, level rotary. Okay. Right. So people use yeah, L or kind of yeah, use minus sign okay, indicated okay. So yeah. And so yeah, quite often when you purchase some kind of chemical, if it's kind of chiral, okay, so you quite often see this kind of yeah sign, okay. So if the D or plus as indicated of yeah, this molecule can rotate plan polarized like kind of clockwise, okay. And then if yeah L and then the minus rotate kind of yeah yeah counterclockwise, okay. So that's yeah something please keep in mind, okay. All right, and so one interesting is kind of yeah, for two enantiomers, okay, mirror imaging, non-superposable, okay. So the rotated plan polarized light kind of the same degree but opposite direction, okay. So one's kind of dextro rotary, okay, another one has to be kind of level rotary, okay. So for example, okay, so yeah, here a pair of enantiomer is kind of lactic acid, another one kind of R lactic acid, okay. So you can see kind of yeah, one rotate kind of plan polarized light kind of yeah, this here plus, okay, and then that's here the dextro rotary, another one will rotate kind of yeah, minus level rotary, okay. So yeah, that's here yeah, very important for the kind of pair of enantiomers, okay. And please just keep in mind, okay, so there's no relationship between kind of rotation kind of direction with RS, okay. So yeah, for example, case one pair of kind of enantiomer, okay, so then R may be rotated kind of clockwise, S rotated counterclockwise, okay. But another pair, okay, different kind of pair for enantiomers, okay. R may be rotated kind of counterclockwise, S may be rotated clockwise, okay. So that's why when you see kind of chemical labels, okay, so yeah, quite often the people label both kind of enantiomer kind of RS and also plus and also minus for the plan polarized kind of directions. Okay, so that's they are different. Okay, so that's just really depends on the measurement. Okay, for the plan polarized right kind of light rotation directions. Okay. Right. So like I said, kind of we can actually quantify kind of degrees case for certain chemicals okay, for certain kind of chemical molecule okay. So that's introduce kind of specific rotation okay. That's actually kind of most important kind of the concept we have to learn today okay. So this one actually similar like in the melting point, boiling point for one compound okay, and then different kind of chemical molecule has different kind of specific rotation okay. So that's rotated plan polarized light. Okay, right, and so that is depends kind of what is liquid. Okay, so if the solution it has one formula, if it's kind of pure liquid, it will have another equation. Okay. So just keep in mind, okay, so normally the sample size for the parameter kind of 1 decimeter, 10 centimeter, okay. So that's we use for the length, okay. And this because kind of most important case so that I'm going to kind of write it here okay so that specific rotation, right. So we first do the liquid one case so first do the solution okay. Solution means you dissolve your solid sample or maybe liquid sample in some kind of organic solvent and then matter is kind of plan polarized light okay. Right. So for the solution, it's formula like this, okay. A times kind of here the alpha, and then say times L. Okay, so we do explanation one by one. Okay, so this is kind of specific rotation. Okay, this one. Okay, so and someone maybe notice another T and also lambda. Okay, so T is kind of just here the temperature. Okay, and lambda is kind of wavelength. Okay, so what wavelength kind of light you strike the sample. Okay. So normally T is just kind of room temperature. Okay, I just use R and T. Okay, and the wavelength. Okay, so normally people use sodium lamp. Okay, so that people label as kind of D. Okay, so that's indicate of sodium lamp kind of wavelength. Okay, all right, and so more important here. Okay, so so this alpha is kind of observed rotation. Right. So that's actually measured by kind of polarimeter. Okay, polarimeter give our kind of reading here. Okay, and then this L is kind of cell length. Okay, so that's here the sample cell. Okay, and so the most important thing kind of here. Okay, so units kind of decimeter. Okay, decimeter. Okay, so 10 centimeter. Okay. Right. So the most important actually comes kind of the concentration. Okay. So this is concentration. So the concentration of the unit here is kind of very special. It's gram per 100 mil. Right. So that means kind of 100 mil solution. How many gram of solid? Okay. So or maybe liquid. Okay. So dissolve in the 100 mil. Okay. So please keep in mind this is a very important. Okay. So quite often student make mistake because mess up kind of units here. Okay. Right. So that's about pure solution. Okay. And the next one's kind of pure liquid. So liquid kind of actually a formula is much easier. Okay. So still do here. Right. So here is still specific rotation, and then this alpha is kind of observed rotation. Right. And then this L is still the cell length. Unit is still decimeter. And then the only difference is here, actually kind of another difference, kind of no 100 here, no 100. Okay, so solution has 100 times kind of alpha. Okay, so observer rotation. Here is kind of no 100. Okay. Another difference here, okay, so we don't use kind of concentration. Okay, so we use this kind of density of this liquid. Okay. So that's pure liquid. Okay, pure liquid density. Density, the unit is kind of gram per mil. Yeah. Okay. Right. Make sure you guys kind of write it down. Okay. So that's actually kind of most important kind of formula for today's kind of class. Okay. Yeah, we come back. Okay. So here I also show these two formulas on the PPT file. Okay. So All right. And then next kind of I will give you a couple example. Okay. And then calculate kind of observer rotation and those specific rotation. Right. Right. First one is kind of sample of pure ice two butanol please kind of 1 centimeter kind of parameter tubes and use the D line as sodium can lamp and then ask kind of what's observed rotation at the certain degree the kind of 104 and then density of this pure liquid kind of 0.805 and gram per mil and what's specific rotation for this the liquid and so for this question so how do I say both right. Can you guys see both my slides and those the document camera? Okay, good, good, good. All right, that's good. Good. All right, so once you guys can see both, okay, and then I can, okay, so I can, do some kind of math, okay. All right, so here, okay, so anyway, okay, anyway, okay. So if you guys cannot see my kind of document camera, please let me know. Type in the chat window, okay. And so here, okay, so you first need to know which formula to use, okay. And so here's kind of pure liquid, okay. So that means we need to use the pure liquid formula, okay. So specific rotation equals kind of alpha and divided by kind of density times kind of length of cell, okay. All right, so next kind of we just plug all the information inside of this formula, okay. And here, already told you kind of the observed rotations kind of the 104, okay. Right. So please keep in mind you need to keep here the plus or negative kind of minus sign, okay, 104, okay. And then the cell length is the 10 centimeter, okay. So 10 centimeter, okay. So equals to kind of 1 decimeter, okay. So then that's just 1 decimeter here, okay. And then the density of this compound is kind of point here the 805 gram per mil. Okay, so right, and then that's all the information we already plugged in here. And then that's ask kind of for the spectral rotation. Okay, so then that's you just get your calculator. Okay. Right, so there's the one, okay, and then eventually, okay, so that answer should be the plus 129 degrees. Yeah. So that's how do you work on this, okay? Right, and then we do another one, okay, so little bit harder one, okay, so Okay. So next one's kind of the calculated this time kind of the solution. Okay. So 0.5 24 gram of S 1 amino 1 phenylethane okay, diluting the solution. 10 ml of methanol in 25 degrees okay. So then in 1 decimeter tubes okay. And ask this one already told you kind of special rotations minus 30 degrees okay. Ask kind of observed rotation okay. Here keep in mind ask you for observed rotation. Right, and then this time we will use kind of the solution kind of formula okay. Keep in mind okay. So because this one kind of dissolve one chiral molecule in the methanol solution okay. Right, and then we move into bit hard. Right, so for the solution kind of formula, that's the 100 times kind of observed rotation, and then divided by kind of concentration, and then L. Okay. Right. So for this kind of question case, you need to plug all the information also into this formula. Okay. So we do one by one. Okay. So we do the easy one first. Okay. Easy one first. Okay. So the first the density, the cell length is still 1 decimeter. Okay. So all right. So 100 okay times alpha. Okay. And also told you the specific rotation is the minus 30 degrees. Okay. So this time we know this specific rotation. Okay. So minus 30. Okay. Keep minus 9. Okay. All right. And ask for the what's observed rotation. Okay. All right. So now comes the difficult part. Okay. So concentration. Okay. So concentration for original kind of questions the point 24 gram in 10 ml solution. Okay. Remember, okay, so solution of formula. Okay. So that's in 100 ml. Okay. Solution. Okay. So 10 ml. Okay. So that's times 10. And then you also need times 10 on the top. Okay. So that's and then that give kind of 100 ml should be 5.24 gram. Okay. So in 100 ml, this solid should be kind of 5.24. Okay. So that's the unit here. And then 5.24 you need to put in here. Okay. So because this one asks kind of how many grams in 100 ml, okay, so that you need to do this kind of conversion, okay, do this kind of conversion, okay, right. So now we have all the information 105.24 1 decimeter minus 30 degree, okay, so that's easy figure out what's alpha, okay, so this alpha, okay, so I do it here, okay. So minus the 30, okay, so degrees times 5.24 times 1 decimeter divided by 100. Okay, and then still use your calculator. All right, so that's the 1.57. Okay, so 1.757. Keep in mind original there's kind of a minus sign, and then you need still keep this minus sign. Okay, minus 1.57 degrees. So that's the answer. Okay. Right. Do you guys get it? Okay. Any questions still, type in the chat window. Okay. So the most important thing kind of first, make sure you know which formula do you use. Okay. Second, kind of just put all the non-information in the formula, and then figure out what's unknown information. Okay. And specifically attention to density. Okay. Density. Okay. So and also concentration of solution. Okay. Concentration. Okay. So that's gram per 100 ml. Gram per 100 ml. Okay. All right. So we'll do more calculation later, okay? So don't worry, okay? So yeah. Right. Here's another important kind of the formula, okay? So yeah, optical purity, okay? So yeah, generally speaking, kind of yeah, we want 100% kind of R or 100% S, okay, for one yeah molecule, okay. But yeah, quite often we get the mixture, okay. So yeah, there are some kind of yeah, majors kind of R minus S, or maybe minus kind of yeah, yeah R majors kind of S, okay. And then we will yeah, measure kind of yeah, yeah observed rotation for this kind of sample, okay, with one kind of yeah, give you kind of yeah structure routine kind of yeah reading, okay. So yeah, because that kind of yeah R S will cancel out each other, okay. So because one kind of yeah rotate clockwise, one rotate counterclockwise, okay. And then yeah the real yeah observed rotation kind of yeah should be less than kind of yeah the pure R or kind of yeah pure S, okay. And then here kind of yeah come to formula, okay. So the yeah optical yeah purity equals to kind of yeah observed rotation divide kind of yeah yeah pure sample kind of yeah the observed rotation, okay. So yeah how do I write I just yeah put observed, okay. And then here's kind of yeah yeah pure samples kind of yeah yeah pure R or pure S, okay. So yeah pure enantiomer times 100, yeah, right. And then next the formula, okay, that's here the enantiomer excess, okay. So that yeah, people use a lot in our kind of yeah organic chemistry, okay. So yeah, this here the yeah tell how pure, also how pure kind of yeah this sample, okay. So yeah yeah. So yeah, quite often people use kind of yeah double E percentage, okay, indicate kind of enantiomer per excess, okay. So this one yeah, just here the yeah. You can use here, okay, so yeah, number of your molecule of isomer in excess minus number of yeah, the molecule yeah, of another isomers, okay, so yeah, we have kind of R and S, okay, so yeah, then just yeah, yeah, use R minus S or S minus R, okay, and so yeah, otherwise I can write it like this way, okay, so percentage of yeah, yeah, one enantiomer minus yeah, yeah percentage of another enantiomer. Okay. And so the bottom is kind of total, yeah, number of molecule. Okay, so that's here the we can, yeah, write down at the bottom. Okay, total, yeah, percentage of yeah the both yeah the yeah enantiomers. Okay, so yeah. So normally bottom is kind of yeah 100. Okay, so yeah, that's R S. Yeah, you add them together, it's kind of yeah 100. Okay, so yeah, here. Okay. Right, okay, so now it comes kind of a pretty important conclusion, okay. So reality case, yeah, yeah, optical purity equals to kind of yeah, yeah, enantiomer access, okay. These two, yeah, give same kind of yeah, the information, okay. So that's yeah, also give kind of important thing, okay. So yeah, by measure kind of yeah, the observed rotation, okay. So actually we can calculate kind of yeah, the amount of R or S in the kind of yeah, the mixture of yeah, RS mixture, okay. So yeah, that's yeah something yeah please keep in mind. Okay, so yeah yeah, and I can give you a couple example. Okay, so do I have here? No. Right. Yeah. Here's kind of yeah yeah pretty good yeah form yeah. If you have yeah yeah last page of yeah yeah worksheet, okay, I give it to you guys. Okay, you can take it out. Okay, you can take it out. Okay, so yeah, last page of yeah worksheet. Okay. Right. So now, yeah, we work on the yeah second question. Okay, second question. Okay, so yeah, yeah, use yeah this formula. Okay, so yeah, and let me take this one off. The second question is kind of yeah if with the specific rotation of R enantiomers is 8.4, okay, then what specific rotation of mixture of yeah, 60% R and also 40% S, okay. Okay. So this one actually not hard, okay, actually not hard, okay, so yeah. Uh, we just use these two formula, okay, these two formula, okay, so yeah. All right. So yeah, here already told you kind of pure sample case the specific rotation is 8.4. Yeah, if you guys have any question, can type in the chat window. Okay. So that's here. Okay, actually kind of maybe I write down the whole formula for you. Okay. Yeah, just keep in mind, this two formula give same kind of information. I just put total in the bottom. Okay. Right. So then we can plug the information inside. Okay. So here, okay, so the total is kind of 100%, okay, 60% R, 60%, 40% kind of S, okay, so we still can add, right? And then, one enantiomers kind of 60% R minus kind of the 40% S, okay. So then next kind of just on the right, okay. On the right, okay, told you kind of R, pure sample is kind of the plus 8.4, okay. And then ask kind of what the observed rotation for these two mixture, okay, so that's only information like here, okay, right. So that's we already have all this information, okay. That's just easy to figure out what the observed rotation, okay. So we still can do the math, okay. So that should be 20% divided by 100%, okay. That equals on the two, okay. And here's kind of the 8.0, okay. So then I get you my calculator. Okay, so that's pretty much just point two times 8.4, 1.68. Right. So keep in mind, okay, so R is in the x-axis, okay, so the R is kind of the rotate clockwise. We need to still keep this plus line, and then that's 1.68 degrees. Okay. So that's how do you do this kind of calculation, okay? Right. Okay, and then we move to next question, okay? So question three, okay? So we are asked kind of what enantiomer excess E value or kind of mixture contain 12.8 ml of the moles of R 2-bromo butene and also 3.2 mol of S 2-bromo butene. And for this one, okay, actually also not hard, okay, so enantiomer access we already learned here, okay, actually just directly use this formula, okay, directly use this formula, okay, so this one actually pretty easy, okay. So the total amount, okay, so that's 12.8 plus the 3.2, okay, so that's the total amount, okay, for this two enantiomers, okay, and then measures kind of the 12.8, that's R minus the 3.2, okay, minus, okay, so that actually give kind of the enantiomer excess, okay, so this one. Let me see. I should have the answer. Oh, here. Okay. 60%. Okay. 60%. Okay. So that's yeah, pretty easy. Okay. Pretty easy. Okay. So yeah. All right. And then yeah, the last one actually kind of yeah the most difficult one. Okay. So yeah. Actually also yeah go back to yeah, the yeah here this one. The last one, yeah, yeah, we need to use spectral rotation calculate kind of yeah, the percentage of yeah, yeah, individual components. Okay, so yeah, uh, pretty long kind of yeah, yeah, question title. Okay. So spectral rotation of isoform of yeah, the naproxen. Okay, so it's yeah, yeah, minus 20. Okay, so minus 20. Okay, so that's yeah, we maybe put on here. Okay, pure ice. Okay, the spectral rotation kind of yeah, minus 20 degrees. Okay. And then drug makers is selling kind of selling and naproxen on the internet to save money. The company makes a mixture of the beneficial R form and also inactive S form. Okay, so that's yeah pretty interesting for some kind of yeah medicine. Okay, so yeah yeah only one enantiomer actually is kind of yeah active, another one actually inactive. Okay, so for this case R actually kind of yeah yeah can help you yeah yeah treat yeah the disease. Okay, but S actually kind of yeah yeah not active. Okay. And then house yeah, the kind of matter the kind of sample this year the counterfeit yeah, the naproxen and then find the spectral rotation kind of yeah point 5 yeah plus yeah, the 5 degrees. Okay. So that means yeah yeah keep in mind. So pure ice spectral rotation kind of yeah the minus 20 that means yeah pure R spectral rotation should be yeah plus 20. Okay. So if it's kind of yeah, we know the kind of only R is kind of active. Okay, so yeah, if it's kind of yeah, just the pure R should be plus 20 okay, degree. Okay, but yeah, only not kind of we observe rotation kind of yeah, yeah plus yeah 5 degrees. Okay, so that means kind of yeah, there's yeah, some yeah, the ice yeah mixed with R. Okay, cancel out some kind of yeah, R. Right, so that's why it's kind of only 5% kind of yeah, yeah observed. Okay, that's kind of mixture. Okay. Or ask kind of yeah, the determine kind of yeah, the optical purity of yeah, this yeah, yeah, counterfeit yeah, the naproxen. Okay, what's relative amount of yeah, the RS in the mixture. Okay, so yeah, this is a pretty good example. Okay, and then yeah, we still can use yeah, yeah, kind of yeah formula I just yeah showed you guys here. Okay, so yeah, so that's observed rotation, and then here's the pure rotation. Right. So observed rotation is kind of yeah, yeah 5 degrees. And then pure is kind of here the 20 degrees. Okay. And then we can get here the yeah optical purity. Okay, optical purity. Okay. So that's optical purity if you do the math.
Hey,
Okay,
Dr. Leo,
file. Yeah.
your page of example was like above the view, so nobody could see anything you wrote for the last 5 or so minutes.
Oh, I'm sorry. Okay, so yeah, I'm a little bit lower. Can you see it now?
Yes.
All right. Okay. All right. So we go through it again. Okay. So pure ice is kind of yeah minus 20. Pure R is kind of yeah plus 20. Okay. So yeah, because it's kind of yeah pure. And then we observe kind of yeah, yeah, plus 5. Okay, so that means kind of yeah, we have more R than S. Okay, more R and than S. Okay, and then we can use yeah, optical purity. So this formula, okay, so yeah, calculate kind of yeah, yeah, E value. Okay, and then further figure out kind of yeah, what's potential each. Okay, right. So that yeah, yeah, just yeah, yeah. Observe divided kind of yeah, pure sample, that's yeah, 25%. 25%. Okay. All right. Okay. So yeah, here for okay, how do we figure out kind of how much kind of R or how much S? Okay. So actually, we can use some kind of yeah, some kind of math. Okay. So yeah, that's yeah, a little bit hard. Okay, but yeah, you can do this. Okay. So we have R, okay, minus S, okay, so yeah, and then R plus S, okay. R plus S is 100, okay, R minus S kind of yeah. We're assuming S is kind of X, okay. And then R will be 100 minus X. And then bottom kind of 100, okay. So you can solve this formula, okay. So and then easy one, okay. So that's yeah, easy one, okay. So the 25 percentage actually kind of just yeah, all from R, okay, because yeah, this R is kind of give this 5% kind of degrees, okay, and then what left over, okay, so that's cancel out, okay, R and S, okay, so yeah, left over should be 75, okay, so left over is kind of R plus S in 1-to-1 ratio, okay. So yeah, because you have RS kind of cancel out, okay, so that's why kind of won't show this kind of the spectral rotation, okay. Only the 25% can R actual 25% R show 5%, okay. And then then that's pretty easy, okay. So because R plus S is kind of the 75%, okay. Then if you do some simple math, should be kind of 75 divided by 2, that's here the 37.5 percentage. Okay. So that means kind of here the mixture, you should have kind of here 37.5 R and then 37.5 S cancel each other's. And then actual kind of 25% kind of R, okay, so showed here, okay. And eventually, okay, so that's the pretty easy, okay. So you add 25% kind of R and then to 35, 7.5 kind of the percent R, okay. So that's your total R amount. And then another kind of just 37.5 kind of S, okay. So that the answer should be R, we have 62.5%, S 75.5, okay. So that's the final answer, okay. So this calculation kind of pretty hard. Okay, so I won't show you guys in the kind of the future exam the quiz. Okay, so be safe. Okay, so but question 2 and 3. Okay, so last two I will maybe test in kind of future exam quiz. Okay, make sure you know how to kind of calculate the optical purity, how to calculate the enantiomer excess. Okay, so that's please keep in mind. Okay. All right, okay, and then some kind of concept, okay, so the racemic, okay. So racemic kind of 1-to-1 ratio of RS mix them together, okay. And so because RS one rotate clockwise, plan polarized light clockwise, one rotate kind of counterclockwise, okay. They will cancel out each other, okay. So racemic actually similar like the A chiral molecule, okay. Spectral rotation should be 0, okay. Spectral rotation is 0, okay. And so most time people if you purchase some kind of chemicals, okay, people label kind of D, comma L, okay. So that means kind of rust mixture, okay. You have RS kind of 1-to-1 ratio, okay. Or sometimes you see kind of this plus line, minus line together, okay. That's also means rust mixture, okay. So rust mixture kind of last value, okay. Last value, okay. So because kind of only one maybe enantiomer kind of active can treat the disease, okay. Another one kind of actually inactive, okay. In this case, people try all kinds of ways to kind of separate kind of the enantiomer from racemic mixture, okay. You don't get kind of pure R, pure S, okay. There are several ways to do it, okay. So one kind of localization, okay. And so you use another kind of pure enantiomer, okay. Try to localization, okay. Try to kind of pure enantiomer, okay. And the second way is kind of use chirochromatography, okay. So that this chromatography actually kind of has kind of chiral molecule on it, okay, and then can bond one enantiomer stronger than another one, okay. In this case, you can separate two enantiomer, okay. Last one use kind of asymmetrical reactions, okay. So sometimes people use also kind of enzymatic reaction, okay. So there are you use one chiral molecule or kind of enzyme actually also chiral, okay, and then react with the rest mixture, okay. Then this enzyme or this kind of chiral molecule can only react with one enantiomer, convert kind of to other molecule, and then won't react with another enantiomer. By this case, you can separate these two, okay. So and give you just one example, okay. One example, okay. Why is kind of the separated the enantiomer kind of pretty kind of the important. Okay. So I did some research try to use the chiral epoxide. Okay. So if I purchase kind of resin mixture, so that's 1-to-1 ratio RS. Okay. $10 100 mil. Okay. $10 100 mil. Okay. So just RS mixture. Okay. But if we want to purchase the pure R epoxide. Okay. Pure R epoxide. Okay. So that's $100 per 1 mil. Okay. $100 per 1 mil. Okay. So that's you see the difference. Okay. So yeah. All right. Okay. So we cannot finish chapter. Okay. So we just stopped here. Okay. So and so later I will post this video online. Okay. And on Wednesday, okay, so we'll have a quiz 4 first, okay. Quiz 4 won't cover the lecture today, okay. Won't cover lecture today, only the lecture until Friday, okay. And then we'll continue finish the chapter 4, and then we'll start new chapter 5. Okay, right. Thank you guys. Okay, so any questions? Yeah, if no further question, I will stop here the video today. Okay, thank you very much, guys. Everyone. Okay, so yeah, thank you.